Imagine an airplane shrunk to the size of your thumbnail. Is that even possible? It is at the Air Force Research Lab.
We are in a program called micro air vehicles. Traditionally, the role of the Air Force has been very large aircraft. So you can imagine an F-16 or an F-22. It's very large. Lately, things have been getting a lot smaller because you want to go sometimes to places that you can't get in with an F-16.
Micro air vehicles, also called MAVs, are the future of collecting intelligence.
A micro air vehicle might sit inside a building. It might sit outside of a building and sit and watch a doorway. And the nice thing about it, because it's so small, it's going to be harder to see the micro air vehicle. The idea is that it can sit there and nobody will notice it, and we can just gather intelligence.
These MAVs will look and fly like small birds, or maybe insects. The engineers actually study real-life birds and bugs to help them in the building process. An MAV has to carry sensors, receivers, and a power supply, and still be light enough for controlled flight. It's a big challenge, but the Air Force has the people and the resources to crack it.
As technology progresses further and further, electronic devices are able to be built smaller and smaller. In this video, we'll be looking at the smallest robots ever built, from robots the size of an insect, all the way down to robots smaller than a single-celled paramecium. These robots are anything but small fry. The very first robot we're going to be looking at, which is also the largest on the list, is the RoboBee built by researchers at the Harvard Microrobotics Lab. In development now for over a decade, the tethered version of this microrobot is about the size of a quarter. The RoboBee is made of carbon fiber and weighs just a fraction of a gram. Capable of carrying a tiny camera, researchers see the RoboBee being used to monitor environmental hazards and for use in search and rescue missions. Not too long ago, the RoboBee saw a major upgrade, equipping it with an extra pair of wings, reducing the weight of its power electronics, and integrating high-efficiency solar cells. The RoboBee is now capable of untethered flight. The newer version is called the RoboBee X-Wing, and although it's larger than its predecessor, it still only weighs 259 milligrams, and there's little doubt that the researchers will be able to miniaturize it even further. Next on the list, coming out of Georgia Tech, we have the BristleBot. This multi-legged robot is made with a 0.3mm thick actuator block with 4 to 6 legs fabricated by 2-photon polymerization lithography, very similar to SLA 3D printing. The BristleBot weighs only 5 milligrams with dimensions of 2 by 1.87 by 0.8 millimeters and has 4 to 6 legs depending on what it's going to be used for. It can move around by picking up vibrations of external sources like a speaker, ultrasound, or sonar waves, or through oscillations caused by the onboard piezoelectric actuator, and moves at 8 millimeters per second. Piezoelectric actuators convert electrical energy directly into linear motion or the reverse, creating electricity from vibrations, theoretically allowing them to power up a sensor. Changing the size and design of the legs allows them to respond to specific resonant vibrations, and connecting two BristleBots of different sizes together allows the BristleBots to be steered towards the desired direction. The BristleBots are capable of sensing subtle changes in the environment, and working together, they can be used to carry heavier objects. Their stated purpose is to be inserted into the human body for medical purposes. The next robot on the list is another millimeter-scale robot, aptly called the MilliRobot. Created by researchers at the Max Planck Institute in Germany, this untethered robot is capable of walking, rolling, climbing, jumping, and swimming. Also intended to be used to transport medication, this robot is much more maneuverable, and a single robot is capable of carrying an object. The MilliRobot is made of a 4mm strip of elastic silicone embedded with magnetic microparticles. By using external magnetic fields, the robot can be maneuvered and made to perform the wide variety of tasks it's capable of. The incredible mobility of the MilliRobot makes it ideal for minimally invasive medical applications inside the human body. Researchers hope to use it to transport medication to the specific areas in the body where it is needed, introducing it into the body either by swallowing the MilliRobot or inserting it into the body through a small opening in the skin. From there, it can move through the digestive tract or through the bladder to get to where it needs to be. One goal is to have the robot perform diagnostics and therapy in areas currently inaccessible without a scalpel. The BubbleJet microrobot, also created by researchers based in Germany, is smaller than a millimeter, its dimensions being 0.8 by 0.8 by 0.14 millimeters. The robot is made from such flexible materials that it can be bent and deformed without breaking, allowing it to pass through capillaries or other small channels in the body. More development is needed before it can use its propulsion system to navigate through the body, as it currently requires a solution of water and hydrogen peroxide to move. The robot has 2 rolled polymer tubes that run lengthwise along each side of the body, and a small amount of platinum that coats the inside of the tube causes a catalytic reaction, shooting out dual jets of oxygen bubbles that provide thrust. According to the lead researcher, if no heat is applied to the robot, only one tube will expel oxygen bubbles, making it swim in circles. If some heat is applied, both tubes will expel equal amounts of bubbles and it will swim in a straight line, and if even more heat is applied, it will swim in the other direction. Heat is provided by wireless energy that is picked up by a tiny antenna, similar to wireless inductive charging. The robot also has a thermal-responsive manipulator arm, allowing it to grasp and to drop tiny objects by controlling the heat. And if that wasn't enough, it also has a tiny infrared LED on board, allowing the micro-robot to be tracked while it travels through the body. The goal is to have the micro-robot provide targeted delivery of medicine, including diagnostic and even surgical procedures. Continuing down the list, it's time to break out the microscopes because the next robots are at the micron scale. The next robot is 40 to 70 microns in length, 40 microns wide, and a height of only 5 microns, a micron being 1/1,000,000th of a meter. The Cornell microscopic robot looks like it comes right out of a science fiction movie. For scale, the robot is a little larger than an amoeba, but smaller than a single-celled paramecium. These are the first microscopic robots to incorporate semiconductor components, allowing them to be controlled and made to walk. Each robot consists of a simple circuit made from silicone photovoltaics, which function as a torso and brain, and 4 electrochemical actuators that function as legs, 10 nanowatts. Because they are made with standard lithographic processes, they can be fabricated in parallel where 1 million robots fit on a 4-inch silicone wafer. Researchers hope that swarms of these microscopic robots could be dispatched to probe the human brain or suturing blood vessels or even restructuring materials. Given the research is supported by the U.S. Army Research Office, an element of the Combat Capabilities Development Research Laboratory, as well as the U.S. Air Force, you'd be forgiven for thinking these robots could be used for more deadly purposes down the line. And now, for some nightmare fuel, here are dozens of these robots being sucked up into a syringe. Now, if that wasn't scary enough, researchers from MIT are developing microscopic robots light enough to float in the air. I won't go into too much detail about these as I didn't find very much material, but their aim is to put microscopic electronic circuits onto tiny colloid particles which are light enough to float suspended in liquid or even air. Their aim is to have the robots carry out diagnostics, from the human digestive system and bloodstream to oil and gas pipelines, and even waft through the air to measure compounds inside a chemical processor or refinery. These robots are about the size of a human egg cell and don't need any external power sources or even batteries. Their circuits would receive all the power they need from a photodiode. The last robots we're going to look at are created by researchers out of the University of California at San Diego. They're tiny ultrasound-powered nanorobots designed to swim through the bloodstream and remove bacteria and toxins. Using gold nanowires coated with a hybrid of platelet and red blood cell membranes, these nanorobots are capable of performing 2 different tasks simultaneously. The hybrid cell membrane coating allows the nanorobots to function as platelets, which bind pathogens like MRSA bacteria, and to function as red blood cells, which absorb and neutralize the toxins produced by these bacteria. The gold nanowire responds to the ultrasound, giving the robots the ability to swim. At less than 2 microns in length, these are the smallest robots on this list. At the time the article was written in 2018, researchers had yet to try them on live animals, and it's not clear if there were any significant advancements since then.
Good afternoon, and thank you for coming to today's MWI speaker event with Dr. James Giordano. Dr. Giordano is a professor in the Department of Neurology and Biochemistry, chief of the Neuroethics Studies Program of the Pellegrino Center for Clinic Bioethics, and co-director of the O'Neill Pellegrino Program in Brain Science and Global Health Law and Policy at Georgetown University Medical Center. As well, Dr. Giordano currently serves as an appointed member of the United States Department of Health and Human Services Secretary Advisory Council on Human Research Protections. He is a researcher and task leader of the European Union Human Brain Project and has served as an appointed member of the Neuroethics Legal and Social Issues Advisory Panel of the Defense Advanced Research Projects Agency, DARPA, and Senior Advisory Fellow of the Strategic Multi-Layer Assessment Branch of the Joint Staff of the Pentagon. It's quite a bit. In his spare time, he has authored over 260 publications in neuroscience and neuroethics, 7 books, and 13 government white papers on neurotechnology, ethics, and biosecurity, and is an editor-in-chief of the International Journal of Philosophy, Ethics, and Humanities in Medicine. Dr. Giordano, thank you for joining us today.
So what we're here to talk about today is the fact that the brain is and will be the 21st century battlescape in many ways. End of story. We could stop it there and I could let you go back to your respective units and think about that for a while, but I'm here to tell you absolutely, as much as there's a big old Tyrolean nose on this face, that you will encounter some form of neurocognitive science that has been weaponized not only in your military career, but in your personal and professional lives, irrespective of whether those two things coincide or not. So the idea of the brain as the battlescape is very important, and more importantly is this other acronym that's up there, which is WMD squared. Please get used to this because this is going to be part of the idea of irregular warfare and ongoing military innovation in your careers. Weapons of mass destruction and disruption. Disruption and influence will be the key to creating peer capabilities and asymmetrical engagements. If we talk about what brain science is, let me just give you a little bit of brief background on this field that is now called neuroscience. As a titular field, as a named field, neuroscience has only been in existence for 40 years. I know that because I've been a neuroscientist for about 38 of those 40 years. When I first applied to get into a program in neuroscience, there were only 4 neuroscience programs in the continental United States. 4. Right now, at this particular point, there are well over 200 dedicated university and collegiate programs, several programs at the junior college level, several programs at the high school level, and many, many dozens of independent think tanks and philanthropic organizations solely devoted to brain sciences. That's just here in the United States. Furthermore, what becomes critically important for you to understand is that brain science is not just a United States enterprise or effort, nor is it singularly an effort of the United States allies worldwide. Increasingly, it is becoming an international, multinational, global, and independently exercised event and endeavor, which increases the capability of the brain sciences to develop not only new theories, but ever more sophisticated tools. I like this slide a lot because what it presents for you, ladies and gentlemen, is a century-long history of brain science, even before it was called neuroscience. More than that, if in fact I understand how it is that your brain does what your brain does, I may be able to access your brain and affect your brain indirectly and directly. And what this allows us to do is to create tremendous potential and possibility and probability, potential, possibility, and probability of what the brain sciences can do and will do. Remember these 3 letters, A, and A. A, the ability to assess the brain and its functions. A, the ability to access the brain on a variety of levels, from the subcellular all the way to the social. And A, the ability to affect the brains and the individuals in which those brains are embodied and the ecologies in which those individuals enact, engage, encounter, from the level of the individual to the group, to the community, to the populational. Look at the power that understanding tools and techniques of the brain sciences afford. It's there before you on the screen. Obviously, if in fact this gives me some insight to the way people interact, inclusive of the way they may interact in bellicose, aggressive, violent, and volatile ways, and it also confers upon me certain powers to be able to influence that, alter that, change that, mitigate that, then clearly I'm able to use the brain sciences, as we have tried repeatedly in the past, to influence the postures and capabilities not only of our own individuals who are engaged in warfare, intelligence, and national security operations, but those who seek to threaten us. In other words, we can utilize these things in national security, intelligence, and defense. The brain is the current and future battle space, or at least one that can be leveraged in those ways to be able to create tremendous effect with fairly little investment of engagement. In other words, what it allows us to do is assess the brain, access the brain, and affect the brain. Generalization, we could parse them down into 2 discrete domains. First, the assessment neurotechnologies that do exactly as the name would imply. They are based upon various tools that we can use to assess those structures and functions of the brain that may be involved in those processes of cognition, emotion, and behaviors. This is what this is about. It's not just a question of trying to figure out what makes the brain tick in the way it's built. It's can we get in there to affect the ticking and talking, and by affecting the way that brain is built and the way it functions, influence in ways that are kinetic and non-kinetic, the attitudes, beliefs, thoughts, emotions, activities, and relative vulnerabilities and predispositions of those individuals for whom both we are responsible in terms of our own forces, perhaps to make them better, more insulated against injury, operationally protected and enhanced, and those who may threaten us. We can also utilize these interventional technologies in those ways that may able to directly affect the brain. Probably the one that you've heard about most recently, most contemporaneously in the literature, is the possibility to use some form of directed energy to affect physiology peripherally and also to affect the physiology and health of the brain. Case in point here, US Embassy personnel in Havana and possibly in China. And of course, there's not a lot that I can tell you about that, although I am one of the researchers on that particular project. But this seems to be wholly indicative and supportive of the fact that this was at least some form of directed energy, whether it was wholly intentional or not, still remains to be definitively decided. However, the pattern of insult and injury to those individuals and the pattern of injury of who was affected strongly suggests that this was an intentional and directed engagement, and that this represents a beta test, a possible probe of a directed energy neuroweapon. We can go further to implant certain brain-machine interfaces. These are many of the DARPA programs that you may hear of now. Probably the one that is most notorious, in a very good sense, is something called the N3 program, which is the non-invasive neurosurgical neuromodulation program being run by their program manager, Dr. Al Mundy. The idea here is to put minimal-sized electrodes in a network within a brain through only minimal intervention to be able to read and write into the brain function in real time, remotely. So, how then can we use these elements as weapons, means of contending against others? Formal definition of a weapon, right out of the Oxford Old English Dictionary. Means of contending against others. And we can do that in a number of ways. We can militate their behaviors and their thoughts in some ways as to make them more amenable to what we do, the idea of positive weaponology. Or we can, in fact, mitigate and in some cases completely nullify their capability, will, or engagement to fight. If we combine those two definitions into one, what we find is those agents that will either change individuals' thoughts, vulnerabilities, volatility to violence and aggression, or incur morbidity, dysfunction, and or mortality in such a way as to then mitigate the engagement altogether. But of course, if we spill over the idea of soft weaponology into a hard weaponization, we also see the use of biodata as a viable weapon. Manipulating biodata so that I can then put into your particular medical records subtle information that may change the disposition of whether you're sick or not, change how you're treated, influence the postures that go to you in terms of insurance, care, viability for military service. By altering that information, by changing those data, by purloining those data, I essentially change the you of you. And I can do that in very subtle and insidious ways. Furthermore, I can do that on a variety of different levels that can affect key individuals, so that in fact your medical record changes to thereby render you incapable or at least invalid to be able to serve in a way you're serving. Or I can do that on a much larger scale, groups, populations. And if I change those data, I change the way you're being regarded and treated. And I can do that in one of two ways. I can do it in such a way that you're going to be regarded in a negative sense, or I can do that in such a way that I'm going to treat you incorrectly. If I say, for example, you have a particular allergy, or you have particular sensitivities, or you have a particular disorder, you will be treated for that, and that could then harm your health and your stability in both a short wars approach as well as a long wars approach. And this is where we get into the idea of novel neuroweapons. Once again, this is not necessarily new, but the momentum of this dimension of the field has accelerated as a consequence of increased understanding of the brain and increased capability to develop tools and techniques to access and affect the brain. So what are we seeing here? Well, take a look. We see in-close neuropharmaceuticals and organic toxins. What's new about this is the in-close nature of this. Increasingly, we're not seeing these things as weapons of mass destruction against gross aspects of the population, although certainly many neuroweapons such as sarin gas and VX and other forms of neurotoxic agents can be leveraged against large groups of people, but that's messy. More specifically, perhaps, might be targeting individuals on a level that allows either direct attribution or covert engagement with non-attribution. Let me give you an example of what I mean. So this gentleman is the leader of some group, a political group, a social group, a combative group, and under the veil of a white flag, he and I are now to have some kind of a caucus, a meeting. And during that meeting, what I do is I lace the rim of his drink, or his pen, or his seat, or something in his immediate environment with very, very low dose drug or toxins that are going to affect his stability. They may affect the way his brain works, and as a consequence of that, they can affect the functions of his brain, his thought patterns, his relative emotionality, and the behaviors that go along with that. One of two things might happen. He might be completely incapacitated as a consequence of this, or he may change his level of capacity and engagement so that he went into the meeting thinking, I hate this guy's my enemy. He walks out of the meeting going, I love this guy's great. Now what could happen? If in fact this is a gentleman who has charismatic, financial, elected, or dictatorial power, it may be that his followers will then follow him blindly. He came into the meeting as a leader of those followers who were bellicose, who were volatile, who are violent and aggressive. He comes out of the meeting and he tells them to change their behaviors, and they do. Or I could sever the trust. By now, he leaves this meeting, he's espousing a very different philosophical stance and orientation, and his followers no longer adhere to his precepts, his tenets, or his lead, and I fractured the relative arrangement of trust, engagement, capability that he fostered, leaving that population disrupted and vulnerable to intervention, to a coup d'etat, to a junta, to some type of insertive reassumption of leadership. You see how this can work? Furthermore, I can use this very tactically. Some of these agents allow me to assemble the agent on site and not have to stockpile it, which allows me to take the components of this agent into and out of a country relatively covertly, target a specific individual, change or eliminate that individual with very little attribution and trace, and be able to leave prior to any attribution. Think Novichok. Or I could assemble very small quantities of this that would then allow a specific intervention, characteristically in a place that would not allow such an intervention. Think of the use of a derivative of Vx in an airport. But I could do more than that. I could also incur much broader type of ripple effects. And one of the ways I could also do that is with what's called high morbidity neuromicrobiologic agents. It's a real fancy way of saying neurobugs. But high morbidity neurobugs. What can I do? I can use a particular bug that I may be able to now modify through the use of gene editing technique that is ubiquitously available and fairly easy to use to take a bug that was previously relatively benign and non-pathogenic and make that bug virulent, pathogenic, dangerous. And then what could I do? I could introduce that bug in key sites. Des Moines, Seattle, Tampa, Newark, Houston. I'd get a few people sick. I'd do it on an airplane, do it at an airport, do it at a sporting event, do it on Black Friday. And then what I would do is I would take credit for that, but I'd want to make sure that at least part of the symptomatic constellation was not only neurological, was profoundly psychological. Agitation, debilitation, sweating, stomach problems, sleeplessness, cardiac problems, things that are what we call top-down neurological in their effect, brain to body and body to brain in the bottom-up cascade. I can disrupt an individual from the level of their cell to their system and disrupt individuals on a variety of levels, from individuals all the way up to the social fabric. One of the newest developments is that nanoparticulate matter can be stabilized for distribution. If you're not aware of what nanoparticulate matter is, it's that matter which exists on a scale of 1 × 10⁹. Very, very small. Smaller than a cell. And we can manufacture materials that have discrete properties that can be controlled by virtue of bioengineering and their physical chemistry. To auto-aggregate, to be able to aggregate in particular areas based upon their biological and or chemical sensitivity. But now we go one step further. Most recently, just a few weeks ago, it was announced that you could then aerosolize nanomaterials. And go one step further, I can create small robotic units, controllable robotic units at the nanoscale, and that these too can be aerosolized to create a nanoswarm of biopenetrable materials that you cannot see, that can penetrate all but the most robust biochemical filters, that are able to integrate themselves through a variety of membranes, mucous membranes, and wherever, mouth, nose, ears, eyes, can be then uptaken into the vascular system to create clumping, can affect the vascular system of the brain, or can directly diffuse into the brain space, and these can be weaponized. And they can be done in such a level that their presence is almost impossible to detect, and as such, the attribution becomes exceedingly difficult to demonstrate. How much of this material would I need? Take a look. This is the front of my pen. This amount of nanomaterial, if be able to maintain and sustain with regard to its deliverability and aerosolization, could in fact affect all of you, or based upon where I come from, New York City, all yous. Look at this. Look at this. I'm carrying that material. Would you see it? Would I have to lug a giant weapon into the room? No, I wouldn't. And what if, in fact, I utilized some form of an unmanned aerial device or unmanned ground device as a delivery vehicle? Something like a drone or a bug. Could I do something with that? But let's keep going. Could I also utilize a whole host of devices to be able to affect individuals close in, for example, during interrogations, during social engagements, during human terrain team engagements, or more remotely, in a room, in a theater, in an airplane, in a bus, in a store, in a mall? The answer is increasingly yes.